Our next presenter is Dr. David Donnet. He has obtained his PhD from University of Glasgow in physics. He was a senior failure analysis engineer at Philips NXP Semiconductor Netherlands from 2000 all the way up to 2010. He has joined Thermo Fisher Scientific as an application specialist in FIB Dualbeam in 2010 and currently is application manager for semiconductor customers in EMEA region. He will focus on beyond GA applications for semiconductor materials and devices with Dualbeam. With that, I'll hand it over to our speaker, Dr. David. Over to you, sir.
Good morning, everybody. Good afternoon.
Good afternoon, Doctor.
I will just share my screen. Thank you for the invitation to talk to this large group this afternoon, everybody. And thanks for the introduction, Lawrence. As I said, my name is David Donnet. I'm from Thermo Fisher Scientific, and today I'm going to talk a little bit about some further applications and some further developments in the realms of FIB. So I think we've heard on the first couple of presentations a lot about gallium applications in standard FIB and Dualbeam. And today we're going to look a little bit further. Some of you may already be aware of these techniques, but I'll try and go into a little bit more depth and provide some information about what really is possible in the next few years. So just a little bit of background. I think most of the audience are aware of this. What a Dualbeam is. So Dualbeam consists of an SEM and a focused ion beam together, and important, of course, is that the beams coincide with each other at a single point. This really allows us to do all sorts of analysis, especially in semiconductor failure analysis. So as you've seen in the previous talks, we can make a cross-section with the ion beam, a very site-specific cross-section, so that we can reach a buried layer or a defect very accurately. And then, of course, we can image that directly with the SEM. As we've also seen in previous talks, if we have a manipulator on the Dualbeam, we can extract biopsies from the bulk, and we can make transmission electron microscope samples. In addition, we have what we call gas injector systems and many other peripherals, but we'll come to that a little later. So if we think a little bit fundamentally about Dualbeam basics or the ion beam basics, there's a couple of things we need to take into account. The first is, for any ion beam system, we need to be able to control the ion beam spot. So here you can see this is a spot burn of a gallium, a large current. I think this is a 65 nanoamp spot from a gallium beam. But you can see it's perfectly round. It's very small, 4 microns. And this is very important. So when you're considering a FIB purchase or a Dualbeam purchase, many suppliers will tell you how large their beam current is. And that's indicative, but it's not the only issue. It's how much current can I fit into the spot. So we need high current densities. And we need, of course, completely symmetrical spots. And we also need to maintain such spots. It's not simply good enough to be able to do this once. So nowadays we expect automatic column alignment of focused ion beams so that any user can achieve the best results. So once we have a control of the spot, we need to control where we put the spot. So we need a very sophisticated patterning engine. And basically what that means is that we want to remove material where we place the pattern. So you can see in this pattern, this is a serpentine, and we're able to mill exactly where this serpentine was drawn. And that only comes about because of certain features on the ion column, such as time of flight correction and also differentially pumped columns. We need to be able to mill different types of materials. We need to have different types of patterns. So a box pattern, cross-section pattern, we need to be able to mill lines, circles, all sorts of things. And we need flexibility to allow users to modify these patterns so that they can remove material or deposit material to meet their individual needs. The third prerequisite is gas chemistry. So we need a range of chemistries associated with the ion beam that allows us to deliver precursors very close to the surface and allow, in this, as we see in this picture, deposition. So this is a kind of wagon wheel on an SRAM cell so that we can probe the SRAM cell. But we also need special chemistries so that we can preferentially etch or selectively etch one material over another. So these are maybe the three prerequisites you need to think about ion columns for failure analysis techniques. Now, the gallium FIB or the gallium dualbeam is so well established in the semiconductor industry. I think since the early 90s, there have definitely been focused ion beams around. And if we think of the applications, well, actually, if we look to the right first, and the last speaker talked about circuit modification or circuit edit, this was actually the original application for focused ion beams. And why is this important? Well, this can save companies thousands, millions of dollars sometimes by able to modify a circuit locally and check the correction of the device before actually making new masks and putting it through the silicon fab for 6 to 8 weeks, only to find out that the correction was incorrect. So circuit edit remains an extremely important application for semiconductor companies. But perhaps maybe more mainstream, the first one is cross-sectioning. We've seen many examples of cross-sections this morning. And here is another high-resolution image. And what we can do is we can locally remove materials to find hidden defects, to find processing errors, which is then followed up with high-resolution SEM imaging. To take that one step further, when we need truly high-resolution information and we need elemental information, then we do TM lamella prep. And TM lamella prep is maybe the most popular application on the dual beam. There's upwards of, I think, 500,000 lamella made in Thermo Fisher systems per year across the world. So this is something customers are doing 24/7, and nowadays they're doing this completely automated. But of course, customers want more. They want to be able to image at high resolution, but they want to be able to remove huge amounts of material as well, not only looking at the silicon device, but also looking at the package. So there's been, over the last few years, or the last decade for sure, an increase in packaging complexity. We've seen the introduction of through silicon vias, multi-die stacks, and basically that requires failure analysis to be done on a different scale. Instead of being able to remove tens of microns with the gallium FIB, now we're being asked to remove hundreds of microns with the plasma FIB. So this is really a change in a paradigm. This is a very simple example here, but one that comes up often. This is a solder bump or solder ball that has been cross-sectioned. Now, if you try and do this in your gallium FIB, you will be there all day. If you put this into a plasma FIB, you can be finished in well under 1 hour. So that really does change or move the dial. It makes it much easier to do analysis on huge structures. So I'm going to explain a little bit about what a plasma source is and compare it to liquid to metal source, which most of you will be familiar with. So it's a parallel beam source. I'll compare in the next slide. So gallium source is a point source. And we have a xenon gas supply that is fed into the plasma cell. We add some energy through an RF generator. We can extract electrons from that, and then we accelerate down the column the ions. It has some simplicity compared to gallium source. We never need to heat the source. It's always on. We simply open the gun valve. So in that way, it's very convenient. But it is rather different from a liquid metal source, a gallium source. So just a couple of comparison. So we're going to talk mainly today about xenon. It's much heavier. It's a different type of source. And on the next slide, I'll discuss a little bit more. But the resolution on a gallium source is around 4 nanometers. It depends how you measure it, but between 3 and 4 nanometers is a good value. For a plasma source, really 20 nanometers for current technology is about the limit of resolution for a plasma source. However, if we look to the largest current that can be attained, that's somewhere between 65 and 100 nanoamps on a standard gallium, whereas in a plasma FIB, we can go up to 2.5 microamps. The result of that is that we can, instead of being able to remove tens of microns of material, or say a cross-section, we can remove hundreds of microns. This slide is perhaps the most important slide to take away when you want to think about the comparison between gallium FIB and plasma FIB. So this is a graph of spot size against beam current. So you'll notice that for most use cases, up to about just under 100 nanoamps, the gallium spot size is dramatically smaller than the plasma in red. So if you think about, if you have the same beam current, let's say that you have, pardon me, if you have a 100 picoamp beam current on your gallium FIB, the spot size for the same current in a plasma FIB is roughly 5 times larger. So this is very important for certain applications, especially, and we'll come to that, especially for TM lamella preparation. But this is really, this is the most important parameter when you're trying to compare the two sources. So we can summarize the spot size. For very small spot size, we could use it for imaging, although of course nowadays we have the electron beam. We can polish, but mainly we're using it for milling or large area removal. I'm coming back to looking at spots because for the plasma FIB, it really is tremendously critical. Because you can imagine if we have a beam of a microamp or larger, we are never going to use that beam to image any material because it will just destroy the material with one scan. And that affects how we're actually going to align the column. So we're going to align the column for the very high spot sizes to be efficient for material removal and not for imaging. So again, I come back to the spot, and there are 3 parts to the spot. There's a core, there's a skirt, and there's a stained area that we don't need to worry about. This is just cosmetic. But we need to think about the core and the skirt. They should be as close to the same size as each other. They should be concentric with each other, and they should be round. And we're able now to align the column in a semi-automated fashion, or soon be a fully automated fashion. And when we align the column, then we get these beautiful spots, even at the highest beam current. So these are spots for 200 nanoamps, 500 microamp, and 2.5 microamps. And really, if you look at 2.5 microamps, you can see it's almost the same size as the microamp. That means we're getting somewhere close to 4 times the current density in this spot. So we can remove enormous amounts of material. And when we have these beautifully aligned spots, we're able to make such a cross-section. So this is a artifact-free cross-section. There is no milling outside of the area of interest. It's a very sharp vertical face of the cross-section. And this tells us that the alignment of the column is very good. So initially, the first plasma FIBs were single beam, so no electron column. And that was somewhat limiting in the applications we could do. We could remove large areas of material. As you can see here on the left, this is a cross-section of a through silicon via. And we could image that with the ion beam, but you can imagine imaging with the ion beam is not ideal most of the time. The other application was what we would call silicon trenching. So for maybe multi-stack die analysis, we could mill through one of the dies very efficiently in 10 minutes or so to access lower dies. But of course, people, again, they want more. They want to have the plasma FIB in a dual beam. So I think around 7-8 years ago, we added an SEM to transform this plasma FIB to a dual beam. We're now on the third generation of this, although it's called Helios 5. And this now offers a wide application space. And I'll talk about some of these applications and show some examples. Of course, this is based on the very popular Helios platform. So we can kind of split the application space into three: process and design analysis for advanced ICs, where we can make huge cross-sections either of the device or including the package. We can also, and I'll show later, we can delayer such devices. 3D NAND is really a focus area at the moment, and I'll explain how we are attacking this application space with a special system. And of course, advanced packaging, 2.5D or eventually 3D packaging analysis. So what are these applications? Not surprisingly, this includes large cross-sectioning, delayering of logic devices, delayering of NAND devices, being able to remove huge biopsies. This is 900 microns long, and in this case, it was used for preparing samples for X-ray tomography. We can do large area analysis, either EDS or EBSD, in this case of a TSV. And we can do lamella preparation, and I'll discuss that a little bit later as well. So you might ask, why do we need high-resolution SEM in a dual beam? And there's three key reasons for this. I'll maybe again start on the right-hand side. Much of what we do is large area cross-sectioning, and we need great SEM detectors. We need to be able to collect all sorts of signals simultaneously, especially collecting backscatter signals where we can really look at the materials, and this is intermetallic compounds and such at the solder ball interface. We need high-resolution SEM to be able to endpoint TM lamella and cross-sections. So if we want to make high-quality TM lamella, we need to be able to see the feature of interest or see the defect of interest and stop there. And finally, we need great low kV performance, and I'm talking about 1 kV or less, in order to perform proper delayering. So we need to know that we have stopped on the metal of interest and that we don't have any residues of dielectric on top. So if we image such a delayered sample with 2 kV or 5 kV, we can see straight through the dielectric. And of course, we see the metal, but physically the dielectric is still there. And if you're trying to do nanoprobing, then that would be quite an issue. So let's look at these three applications. We'll start off with the large area cross sections. This is maybe the simplest to understand. and is also perhaps the most common amongst users of plasma FIB, not only for semiconductor, but for all applications. So the example I'm going to show is a device related with some very hard materials, some tungsten carbide materials, but we were able to mill 300 wide, 300 microns into the bulk, and 500 microns deep, and we're able to remove that, and then we're able to, if you look on the right-hand side, we can polish that. Even though there's all sorts of different materials in here, we can polish that using something we call rocking polish. So this is a form of off-axis milling for which no extra holders or technology is required, is built into the system. And so that we can end up, after 6 hours for such a huge cross-section, we have this beautiful image here of package and the device. And we're able to, of course, zoom in and take very high resolution images of intermetallics and such like. So static cross sections are really a large part of what people are doing. I'll try and play a movie now. I'm not sure that it'll work over the internet. We can, of course, go to 3 dimensions, and we can do auto slice and view. We can do this over huge areas, over hundreds of microns. And in this case, this was just some images of TSV. But in reality, we can also add EDS analysis and EBSD analysis. And this can be done simultaneously, imaging and one of the analytics. So you really can build up a very clear picture over a huge volume of what your device or what the package looks like. So that's cross-sectioning. Delayering is perhaps not as well-known a technique, but this is very, very important for advanced IC failure analysis. Previously, people would be delayering devices by hand, so mechanically polishing. But for the most advanced process technologies, it's just too difficult. You cannot mechanically polish a 7-nanometer device. So if we think about the buildup of a device, we break down the delayering into 2 sections. So the top section we call TLR, which is simply thick layer removal. And then the bottom is called the DX delayering, where DX is our proprietary gas, which allows uniform delayering over large areas. The TLR, in most cases, that could still be done mechanically, but the skill of mechanical polishing is slowly dying out. So many labs still have this capability, but many labs don't, especially new labs. But now we're able to offer local removal of these layers also in the FIB. So these top 3 layers show what that looks like. So we start off, we have 3 thick layers of 3 microns down to 500 nanometers. And we use a mechanical technique, or let's call it a sputtering technique in the FIB. We call this spin mill. This is a glancing mill technique, and we can evenly remove these layers. So we can see this is the starting position. This is halfway through, and then we're now removed all the thick layers, and we're into what we call the mixed field region of low K dielectric and thin metal layers, copper layers. Then using DX and the plasma beam, we can then delayer that over up to 100 microns, depending on the technology, and we can go all the way down to contact level. And generally, this is a setup for probing, for nano probing. So we're able to delayer. We can stop on any layer we wish, or we can go down to contact level for transistor probing. So this is a small automation. It will take a little bit of time. This was a 14 nanometer device that we delayered over 50 by 50 microns. You can see all the different layers come up. I'm sorry, I need to drink. And you can see we can delayer that very uniformly all the way down from metal 9 all the way to contact level. And this is something that is simply not possible in the gallium FIB. Although delayering started in the gallium FIB, it's limited to an area of maybe 10 microns, even for advanced processing. And of course, you do not want to go down to transistor level because we've been planting gallium into the channel and we will get a BT shift. So we never really know what we are measuring. So this is something where plasma FIB has really taken over. And some customers purchase a plasma FIB simply for delayering. So as I said, we can use the plasma FIB to prepare for nanoprobing. So in this case, we delayered a region of about 100 microns, and then it was probed. The same probing was done at the four corners and in the center. We see that there's a high planarity of the delayering itself, and that there was no damage or leakage when we measured this in an SEM-based nanoprober. So we have presented a couple of papers and some work at various conferences to show that this is really a valid technique for nanoprobing. And this is accepted in the semiconductor world, and as I said, many customers using this as a preparation for nanoprobing. So just a couple of slides on TM lamella preparation. So the first question always is, can we prepare TM lamella on the plasma FIB? And the simple answer is yes. However, if lamella preparation is your focused application, you should perhaps not be purchasing a plasma FIB. So yes, we can make high quality sub 30 nanometer lamella. This is a FinFET device made in the plasma FIB. But it does take more time and more care. Because if you think back to the graph that I showed earlier, in order to get a very small spot and in order to remove tiny amounts of material to get a very thin lamella, we need a very, very small beam current in the plasma FIB. So whereas you might finish a gallium FIB with maybe 100 picoamps, we need maybe to think about 20 picoamps, 15 picoamps with the plasma FIB. So high quality lamella is possible, but not if you require high throughput. So if you need to do this 24/7, still stick with the gallium. But if you need occasionally to make a high quality lamella, plasma FIB can do it. What the gallium FIB cannot do is lift out 500 or 600 microns of material. So in this case, we've lifted out about 500 microns. We've attached it to a grid. And then if you can see, we've made windows. So actually we have about 8 TM lamella on this one sample. So we can get lots of statistics, and we've made maybe 8 samples in around 5 to 6 hours. So it can be very efficient. And this is something that's really not possible in the gallium FIB. And the special use case is plan view TM of 3D NAND. So if you think to the previous slides where we discussed delayering, we can use the delayering concept for TM lamella preparation. So we go through the usual procedure of making a plan view TM, and then we can remove layer by layer of the 3D NAND until we're at the layer we want. And this, in the end, provides a huge area. This is about 30 by 15. That is very difficult to achieve by normal circumstances. So again, this is something where the plasma FIB really takes over. So that's just a short overview of what you can do for TM prep. Really is possible, and there's a couple of nice examples that gallium cannot do. So that's the main applications for semiconductor industry in plasma FIB. But let's now look a little bit to some new developments, what's happened in the last year or so. which may be of interest for everybody. So until now, I've been talking about what we would call in Thermo Fisher small dual beam. But for the 3D NAND world, we've now expanded the footprint. So we now have plasma FIB on a wafer system for wafer inspection and metrology. And this is a game changer for them because, of course, they can do delayering, but they can really analyze the 3D NAND structure using what we call this diagonal mill. So they can do this they can do this in an automated fashion in many positions on the wafer in a very short space of time and get huge amounts of statistics. So this is really important for the fab industry. And then as well, they can also do lamella preparation, as we discussed, and get very large areas for analysis, and again, huge numbers of statistics. So we're starting to see traction for the wafer version of this within the 3D NAND community. We're also expanding the species. So everything that I've talked about until now has been talking about a xenon source. From at the beginning of last year, we introduced a new system called Hydra, and Hydra has a multi-species source. So the software can switch the species in a matter of minutes. It's just a flick of a button, and you can have xenon, oxygen, argon, nitrogen. And the application space is still being explored. But what's very interesting is that it looks like oxygen source is very good for removing very hard materials. So in this case, this is a piece of diamond, and it's more efficient than the xenon. For semiconductor industry, it could be interesting for removal of or milling of tungsten carbide, silicon carbide, some polyimide type materials. So that could be a use case for oxygen. And for lamella preparation, perhaps not unsurprisingly, finishing off a lamella with argon milling really just produce a better quality lamella. So this is gallium arsenide samples, imaged at 300 kV. You can see on the gallium system, there's all sorts of damage and irregularities. It's a little bit fuzzy with xenon, but we removed all of the damage on the argon film. And these were all finished at 2 kV. So argon could be really useful for making even higher quality lamella preparation. And the final topic I want to talk about today is we have also added a femtosecond laser in the chamber. And the important thing about this is that it is, of course, it's fully integrated in the software, but it is coincident with the other two beams. So now we can do 3D analysis over enormous volumes. Or we can still do 2D, but it allows for 3D analysis, and whether that's imaging, EDS, EBSD, because all three are coincident. And of course, we've integrated an automatic shutter to protect the SEM during the lasering when there's lots of material removed. Everything else on the laser system is the same. We have the same SEM column and the same FIB column. So what does this add? So we really can do real package analysis using the laser. And sometimes we don't need the FIB. So this is an example where we've simply, for the package, we've simply milled with the laser. And, you know, the laser doesn't suffer from charging issues. So some materials that are very difficult to analyze with the Volkswagen beam become much easier with the laser. If we need to polish, of course, we can polish with the plasma FIB. And in the next example, so this is a GPU. So it takes a matter of minutes, I think 8 minutes to remove this amount of material. It's almost a millimeter wide, and even deeper. And that allows us to find the region of interest. And then we can, still over a large area, over hundreds of microns, we can polish, and we can use the rocking polish to find the feature of interest or the defect of interest. And just to finish, I hope this video works okay. We can, of course, do 3D analysis. So this is a 3D volume made only with the laser of a solder ball, a buried solder ball. So I hope that there's not too much lag. It's got some nice voids inside. So this was, 400 slices of 100 of 1 micron thick slices. So this would just be impossible even with the plasma film. So I'd like to summarize what I've talked about today. Gallium applications, the gallium dual beam is here to stay. It will not go away. There are, especially for TM lamella prep, but also for circuit edits, it's very important for the semiconductor industry. But the plasma FIB is now well established. We're seeing it taking traction all over in many labs, and we're now seeing also the wafer system getting traction. Other source species will certainly add new capabilities. This is now being studied and developed for the semiconductor industry. And the integrated laser really does offer an enormous expansion of the volume that can be removed and imaged for failure analysis. So with that, I'd like to thank you for your attention. And if there are any questions, I can always try and answer these now.
So I have a few questions from the audience. Let me open my files. All right. Okay, there's one from Vichin Lok. For plasma, this is related to plasma FIB. Will it damage the sample if you use plasma FIB?
So, of course, if you were to scan the top of your sample with a very high beam current, you could damage the sample. But when you are making, let's say, a cross section or a lamella, then the damage is of the same order as the gallium FIB. So there's been plenty of studies done on this. So the typical damage that we would associate with a FIB in terms of amorphous material is very similar. But yes, if you try to scan with a 2 microamp beam, then it's possible that you may damage your sample. Mm-hmm. So, but you can still scan with a small plasma FIB current. So there's nothing inherent in the plasma source. It's just the beam currents available that you need to be careful with.
All right. This the same question. The same from the same person. What is the lateral resolution of delayering? I think using plasma FIB.
Lateral resolution. I'm not sure what the question means. So. Mm-hmm. Lateral resolution. So we're using the SEM to image what we've done. In terms of area that we are removing, we don't remove layers much smaller than 30 microns. Mm-hmm. But there's no limit on the type of technology that we can delayer.
All right. Okay. This is also related to delayering. I guess you have addressed the technique of delayering using plasma FIB, but the question from Nur Maisara, whether do we need to know the thickness of the layer of interest and control the rate of FIB etching process? So that was the question.
Yes. So I think it would always be wise to understand the process and the technology that you're going to delayer. So either by making a cross section first to understand how many layers there actually are, and the thickness of the layers, because that would determine the beam currents and the high tension that you're going to use for the delayering. So much delayering on advanced processes is done at low high tension. So 5 or 8 kV to control the delayering, because if we're thinking of layers that are sub 50 nanometers in thickness, We need to do this in a very controlled manner, and we can slow the process down by using 5 or 8 kV.
Okay. Okay, there's one question from Zaidi Ambong. What is the difference between FIB and, okay, I have not heard what's PFIB in terms of lateral cross section? Any different? FIB and PFIB. I'm not familiar with PFIB.
PFIB means plasma FIB.
All right. Okay. This is a normal FIB.
In principle, no. So this is a question. I think this is a question that many customers ask. Can we reproduce the same quality of cross sections in a plasma FIB that we do in the gallium FIB? And the answer is yes.
All right. Okay. From Farisal Abdullah. Hello, Dr. David. Does dual beam plasma FIB considered more safer and time effective than conventional FIB?
That depends on what you're trying to do. I'm not sure about what it means safer. For targeted applications, so for large area cross sections, for large area delayering, it's clearly more effective and faster. As I said in the talk, for lamella preparation, it can be very useful, but it doesn't necessarily mean that it's faster. It depends really on the type of lamella you're trying to make it. So for some focused applications, it really is on its own. It's much more efficient than gallium FIB, standard FIB.
Yeah, you've been in this this business of FIB for quite some time, and we know that it is a very useful tools, and a lot of failure analysis lab really have high hope to get this kind of tools. But from your experience, does the industry will later on produce this equipment for a lower cost? I mean, in the future, maybe in 2-3 years down the road?
I don't think the cost will reduce dramatically, no.
Yeah.
These are very sophisticated, complex systems.
Okay.
So I think the typical purchasing prices that you see this now will not drop dramatically.
All right. Okay. So there's one question to our lab. Does plasma FIB available in Myanmar? Currently, no, unfortunately. But we have plans, and we have put some plans to purchase this piece of equipment, and pray for us that everything goes well with the budgets and also the approval. And hopefully we can have this equipment by end of maybe 2022, hopefully, if everything goes well, and then we can serve the industry well with the normal FIB and also plasma FIB. Okay, I think there are still questions pouring in, but I think we would like to hold the question now for time being to give way to Dr. Alexander Bright to proceed with his presentation. Over to you, Lawrence.
Okay, thank you very much. Very interesting indeed. And we have, of course, many questions, as Dr. Shwari just mentioned, but we'll get to them eventually. So just hold on. And once again, I'd like to thank all those 180 odd people who have tuned in to our webinar today. And of course, there are a few up and downs, but now we have about 170 people still with us. So it's good. And do share this video. We will upload it on other social media platforms. You can share it with your friends so that no one has been left